Decided to record a video because there's a lot of very interesting stuff, and I thought it would be worth it. This is not the first time I'm recording this, that's why maybe I will sound a bit annoying. And also, like, there's rain and dog sounds, so I'm sorry about that in advance. Yeah, I got interrupted last time. Anyways, yeah, so basically, as I said before, this entire thing is literally the entire paper. Like, that's it. That's a whole paper. Um, but I don't know, there's a lot of, like, very interesting snippets. Well, first of all, it's just like the cross entropy loss, right? Like that's like super ubiquitous. You already probably know that very well, but I mean, just for the sake of like comparing them, I think it's worth to just go through it real quick. So yeah, as you know, like you just have like a vector x, right? And that's like kind of like look like this, and then you have like your weight matrix, kind of looks like this, right? And then you have like a weight, and then what you do is like just multiply these two things, right? In a perceptron, that's just like x and w. You just multiply them, and that's a logits. So basically, yep, logits like y equals this thing transpose. You can multiply them times x. Those are your logits, right? And then you softmax those logits. So you softmax them, and then what is softmax? Well, softmax is just an exponential function, and then I don't know. Let's say our logits lie right here, um, and then the softmax it will just tell you the heights of these things, right? So it will be kind of like this. And what softmax is doing is like, let's say we care about I don't know, like this one, right? So what softmax is doing is basically just like saying this height over tiny height plus medium height plus, so basically plus the entire height. So right, you think about it, this is just saying like if you sum every single height, you can just get this huge height. I'd say it's kind of like this, right? Um, so if you cared about the middle one, that's this one right here. What percentage of the total? It's this middle point. Let's say this is like 30, right, percent or something, and then this is like 20, and then this is like 50. Yeah, so that's softmax. That's how you can turn it, like basically anything into a probability. And then yeah, once you have softmax, you just have like the loss, right? So the loss is equal to like um, the minus log of the probability with c index, where the c index is the index of the right answer. What does this mean? It's just like if you have like a vocabulary like this, right? And let's say that we know that the next token is b. This is the right one. We first do the logits, right? So you just get like numbers, whatever. And then use the softmax, and then softmax will turn like these logits into a probability distribution. So let's just say that it does something like this, right? Whatever. So yeah, you get this out of the softmax, and then we want to check the right one. So like the right one is in, like this index. So like in this case, it would be index 1, right? So like this index we want. So like you would pull out this one. So if this is like p, then p of c would be the second one. So if you think about it, programming is kind of like this, right? So yeah, like p c equals to yeah. So like this is basically this is just cross entropy. This is like super used everywhere. So that's pretty much how it works. And then yeah, so okay, then the actual interesting thing, which is harmonic loss, right? The first thing that I think is super interesting is well, why is it called harmonic, right? Like harmonic, what where does it come from? Well, that comes from the harmonic mean, right? Um, so you probably remember that there's different type of means. So you have your arithmetic mean, which is just like this, right, over the total, and then you have like your geometric mean, and that's something like this. Well, my guess is like this is the general formula. Maybe this is wrong. I don't. Well, anyways, and then you have like the harmonic mean, which is basically the same thing as the arithmetic mean, um, but it's just 1 over the values, like this. So this is your, which is the same thing as just pulling them the other way around. Um, and yeah, as you probably already remember, oh well, this is gonna be useful right here. So this is where this kind of comes from, which I think is super interesting. Yeah, if you don't remember why this is important, this is like we use this type of means depending on the situation. So for example, like um, I don't know. I think the classic example is like if you have like a car that's doing like 1 kilometer and then 1 kilometer back and then it's going like I don't know like something like that and then like I don't know 20. Yeah. So if you do if you say like what is the average velocity, right? So like velocity average, that's vector. If you do the arithmetic mean, that would be like 30, right? But that's just like, well, obviously not right. So like what you would do is you would get the arithmetic, the harmonic mean, which is just so let's say harmonic, scheiße, harmonic. That would, I mean that would be like 2/1 over 40 plus 1/20, right? And if you think about it, like this is why like this is why it's important. This is why it's used in machine learning, because you're talking about ratios. Um, so like this would be like I don't know like two two over 3/40, and this is like 2/80, right? Which is I mean 3/80, which will be something like 26. And then like, well, you know that harmonic mean is used for like stuff like this, right? So ratios. And that's why it's useful in machine learning, I guess, because like when you're talking about the probabilities, you're basically always talking in terms of ratios. So, I mean, that's where the name comes from, and I think that's very interesting. Anyways, so what this is doing is now, well, so that's the name, and the first thing it's doing this is like redefining the logits, and in this case, before we had like a simple perceptron multiplication, as I said before. So like this would be your logits before, which is then again the simple perceptron. What you're doing in this case is not this, but what you're doing is you're getting the logits is now the distance between your weights and your original value. So like same thing as before. Like let's just say you have your vector right here, and then you have your weight matrix with all your weights. Um, what this is doing is instead of just like multiplying them, this is basically getting the L2 distance between this vector and this weight. So this is basically saying like, let's just say this is the origin, this is your plane. Let's say your x vector is right here, and then your weight one would be I don't know like right here, right? Weight one, and this is just basically calculating the distance between them. And now this is also very interesting because this basically hints at something deeper, right? And what it's the deeper thing that it hints about is like, well, for this to be possible, that would mean that these two share the same embedding space, and that's interesting because that's usually the case. So that's something that I also like. I don't know, just kind of wanted to talk about because that's pretty cool. Um, so if you think about it, like these two have to be related, and interestingly, that's the case also for this one. So like even here, your x and your weights are always related. So then again, if you think about the perceptron, right? So like perceptron, then you have like your weight. These two are always like very closely related. So that's super interesting to me, and that's also like that's a like they share the same embedding space in in like the normal cross entropy and in this new cross entropy. Like it's just the same in both. So that's why they're using this fact to redefine the logits as the distance between these two. Which yes, it's super interesting. And yeah, it's this is the L2 distance. L2 distance basically just means like the square root, right, of the difference. So like I don't know, x minus something like that, or I guess the other way around. but it doesn't really matter. It's just a difference. Um, it literally doesn't matter. But so yeah, that's the difference. So that's why you define the logits. And then this is also super important. If you think about it, right now, if they're like really far apart, their L2 distance will be very high. But if they're like close to each other, it will be basically close to zero. This is super important for like the general algorithm. So like you will see why in a second. So yeah, basically you redefine the logits as the difference. That's pretty self-explanatory, I guess. And then this is also very interesting, right? So like, well, first of all, you're doing this. You're basically replacing softmax by hardmax. So instead of doing softmax, you're doing hardmax. And now hardmax usually it's done as like normal softmax. So like e to the xi over the sum of e to the x's plus an h. So that's usually how hardmax is done. Now this I don't know why they call it hardmax. So like if this is legal, um, but yeah, they basically define their function. So this is basically just doing softmax. So anyways, this is just trying to turn your logits into probabilities. Now this is a different function, of course, but I mean it works the same way. The thing is like before we had um, an exponential function, right? And basically, if you had your logits at certain points, that would be the height. Now, for this case, we know the distances cannot be negative. So basically, you get rid of all these things. So you also you only get positive numbers, right? So our new function basically just works on positive numbers, and our new function, if you like look at it, it's just like 1/x basically, 1/x at some power n. Um, so yeah, I mean, I think I plotted this right here. So this is softmax, like just the exponential, and then this is like 1/x at some with some value. So then again, like this is basically doing the same thing. So like if you get your logits right here, you would just get heights. So yeah, if we go back to this thing, then it would look like this. So then again, if you get logits, now your logits are always positive because they're distances. So like if you have very high distances, that would be like all the way here. If they're very close, that would be all the way here. So you would basically do the same thing. So you just add them up. So you would have your total, which would be, I don't know, two tiny ones, and then there's a really big one. And then, for example, this would be like, I don't know, 80%. This would 0 0.1, 0 0.1, something like that, right? So it's basically the same thing as softmax, just in a different function. That's basically like optimized for our new logits. Now, something that is extremely interesting is like if you look at this function, right? It has an n up here, which is kind of odd, right? At first I was like, what is this? This is called a harmonic exponent. Yeah, it says something random about the heavy tailedness. But if you look at the paper deeply, I don't know if I got this here, probably not. They basically said like n is equal to like the square root of the dimension of the embedding space, which is basically like n equals like 24. Now this is something extremely interesting. The reason why you're doing this, it's because a space, like if you augment the dimensions, the the difference between random points will increase. So this is something very very cool. So for example, like let's say you have like 2D, right? And let's just say like you have a 1 by 1. If you kind of like just plotted like points right here, they would have a certain distance between each other, right? Like just normal points. But then if you have a 3D space, and then you also have like a 1 by 1 cube. So now if you get random numbers between these points, they would be further apart because there's like more space to move around. I think like if you get Gaussian numbers, it's like 1.5 and this is like 1.9 or something like that. But anyways, like as you keep increasing dimensions, the random points will get further apart from each other. So that's super super interesting. And what this term is doing is basically just accounting. So if you look at this thing again, like if you increase d, it basically just like squishes the function down. So this is just accounting for the like the movement in as we increase dimensions. Um, which yeah, I thought it was super interesting. No? So that's this value. To be honest, I don't quite understand why they do this specifically. Should I kind of get it. Like it's just a feeling, but I don't know exactly where this like there's a mathematical reason. Like it's hard, but I don't know how to explain it mathematically to be honest. But I mean I get the feeling, and it does work. But yeah, so yeah, that's basically what this is. And then at the end, you literally get the same thing, right? So like, if you see right here, you get the same loss, which is they say right here, right? Since the step of both losses is the same, comparing their values is meaningful. So yeah, that's super important because now you can just compare them and they would be like apples to apples. So at the end you get the loss, and the loss is just then again the minus log of PC. So like we know that we got these probabilities, and then just as before we just select the probability, like C is the probability of the one we want. So I think we selected the middle one last time, so let's just say the middle one for now. This is like the C index, so this would be the probability of the middle one, so this would be like 0.1, right? um so yeah, that's basically so they're basically like redefining the loss process basically, because the loss itself is not modified, it's just the process, which I mean is super interesting. Okay, so that's basically the entire paper. Honestly, like that's it. Um, now, what they claim is they claim these things, right? They claim it's significantly better at interpretability. Um, which I mean, I I don't necessarily know. I guess so, but yeah. So like they basically claim these three things, like one, two, and three. The first one, like the significantly better at interpretability. I think that's because like you're doing distances and that makes more sense. Like this is just a way more tractable um like process, I guess. Like this just makes sense, like in an interpretability way, like it's just easier to interpret. Now they don't necessarily provide like something specific, so that's my guess. Then faster convergence, I mean these two are related, by the way, so like you will see why these two are related in a second. But faster convergence is actually also extremely interesting. So yeah, they say like, oh, we do toy cases or whatever, and then we get a faster loss decrease, and then the harmonic like y, right? um, and that's because the harmonic loss only requires d to be equal to 0. So this is also something important. So like before, um, like when we have the softmax, right? Let's just do it right here. When we have the softmax, let's just say that we want this probability to be 1, right? So because this is the right label, so we basically want this to be 1. So how do we make this probability 1? Well, you would have to move it to the right, until this is huge. And if this is like ginormous, so let's imagine this is the total sum of heights. Let's say this is the other ones. This would be like 0.999, right? So this is what you want. So this is like yes. um, or I guess, I mean, I think that's understood, but like we can also put it right here, right? So this would be like 0.99, and this would be like 0.05 or something. Anyways, so like if you want this one to be the right one, you would have to move it to the right until um it became bigger and bigger and bigger and bigger. Now, on the other hand, for the other one, you want the distance to be closer, right? So like if they were right here, you want this to be closer. And if you make this point closer, that would mean that the distance would be closer to 0. So like this distance would be closer to 0. Now, if you look at this, right? If you want the probability to be higher, you would want it to be closer to 0. So the distance, this is basically optimizing. Let's say it was right here, and then you have to move it to the left, right? In order to increase the probability. Because it's the same thing as before. Like this is basically the same thing, right? So you wanted to move it to the left until it reaches 0, so that it's the maximum probability, because it would be like huge. Um, and that's why it converges faster. Basically, because for normal softmax, you want something to go to infinity to be the highest possible, and on the other hand, for the other one, you want it to go to zero to go to be the highest possible. So if it goes to zero, it's the highest possible. So this is basically like a set, like a constant. Zero is just a number that you want to reach, as opposed to infinity, which is much much larger. So this basically makes it converge a lot faster. Um, so yeah, that is what it says right here. Yeah, like converging point is to infinity to get the probability equals one, but in harmonic laws, you need the distance to be zero, and of course that makes sense, right? Like if the distance is zero, then you're basically on the same point, so the probability of being in the point is one. Um, so yeah, that's why they do that. So yeah, Gauss entropy loss requires y to infinity to get p equals one. Um, yeah, so that's basically faster convergence. That's also interpretability because like that's the distances. And then like finally is the grokking thing. Well, grokking is this thing where like it basically takes some steps to get to accuracy on the training data, but then it takes more steps to get accuracy in the test data. So that's grokking. They just say it's better. So they just go like, yes, it's better. Um, I'm like, okay. It's just like, yeah, it's better. So I guess so. I don't really know if that's. I don't think it has an explanation other than that. And then yeah, basically, finally, it's just tests. So they train like two normal ones, and then they train two harmonic ones, one MLP, and then two transformers. And they basically like they use this data, they use this test to prove what they claim. Like they use this to prove this. You can see the details on the paper. Like it's, but I don't think that's that interesting, honestly. Like, I think like mathematically and like conceptually, this is the most interesting part. So yeah, that's it.